Okay, and the last time we formulated a proposition about base extension and commuting over higher direct images with base extensions. So let's recall it and prove it. So if we have a projective morphism, and f a coherent sheaf on X, and the dimension of cohomology of fibers with coefficients in the restricted sheaf is constant, so independent of the point in the base. Then the higher direct images, the ith higher direct images of f is locally free of rank C, the dimension of each fiber cohomology, and commutes with any base extension that is for any quasi-coherent sheaf on the base, the natural morphism psi I from the ith direct image of f tensor M into the ith direct image of f tensor the pullback of M is an isomorphism. Okay, so that's what we want to prove. And
I'm sorry.
Yes.
And
yes.
here Fy is the restriction of F on a fiber XY. Yes.
Oh yes, certainly. Yes. Yes.
You write it down as Fy is as a stock. It is not the case here.
No,
yes.
no, it's fiber. It's a fiber. So Fy is well, I don't know how to say it. Iy pullback of F, where Iy is the fiber xy embedded into X. That's what I mean. So it's
Yes, thanks.
a restriction to the fiber. Okay, so now let's prove it. And certainly we deduce it from the Grothendieck theorem we proved last time. Okay, so there is a complex. Well, again, the question is local. On Y, there is a free complex 0 to K0, so on to Kn. to 0, computing the higher direct images of f, and compatibly with the base extensions. Okay, and we wrote down some short exact sequences last time. So let's recall them. We have, say, 0 to...
Извините, а разве такой комплекс не вычисляет правопроизводный функтор тензорного произведения пучка f на обратный образ любого другого пучка G?
Okay, well, I only said it but didn't write it, but let me write it down. Okay. Well, so not quite this complex K, but rather K tensor M. Okay. So these two are quasi-isomorphic. That's what I mean. Probably, I hope that's what you asked.
Спасибо.
Okay. Welcome. So we had the short exact sequences. The image of alpha I minus 1, the fiber at y, goes to the kernel of alpha I fiber at y, goes to the ith cohomology of this complex K, fiber at y goes to 0, and well, it also computed the cohomology. So the right-hand term, the cohomology of the fiber of this complex at y, computed exactly the cohomology of the fiber of our morphism with coefficients in a restricted sheaf. Okay, and from this we deduced that the dimension of cohomology of the fiber with coefficients in the restricted sheaf was equal to the rank of Ki minus the rank of alpha I minus first at y minus the rank of alpha I fiber at y. Okay, and we know that those ranks are upper semi-continuous. We argued this last time, but under our present assumptions, when we're proving this proposition, we will know that the rank of cohomology is constant, and it can only happen if both those ranks of alpha I minus 1 and alpha I are also constant. Okay, otherwise there will be jumps or drops in the dimension of cohomology. So from the constancy of dimension of cohomology, it follows that the ranks of those differentials are constant, maybe locally constant along y. Fine, and now we're almost done. Namely, from this local constancy, we derive that well, that everything we encounter here is locally free. So let me formulate the lemma we are using. So suppose we have a morphism on y, from maybe.
Извините, можно спросить по предыдущей теореме?
Yes.
Откуда следует коммутация с расширением базы?
Well, we didn't prove anything yet. We were close to the victory, but we didn't finish yet. So I will explain. Yeah, I didn't prove yet that it commutes with base extension.
А еще вопрос. Мы уже понятно, почему это локально свободный пучок? Вот правопроизводный функтор от пучка обратного образа пучка F.
No, not yet. So nothing is clear yet. We're close to.
Мы тогда доказали сейчас.
We only recalled that the ranks of differentials alpha I minus 1 and alpha I are constant or locally constant along y.
Спасибо.
But from here, it is already close to the desired statement. So we have a morphism of two locally free sheaves. On y, and alpha has constant rank. Okay, and then I claim that first of all, the image of alpha is also locally free, and hence of constant rank, and locally a direct summand over G, and also the kernel of alpha is also locally free and locally a direct summand over H. Okay, so
I'm sorry, could you help? If you do you mean that if you when you said that alpha has a constant rank, you mean that
I mean
the corresponding
when I restrict it to any fiber, then the rank is so I mean that the rank of alpha y is always the same r for any point in y.
The map between vector spaces alpha y.
Yeah. So alpha y is a map from the fiber of H at y to the fiber of G at y, and these are just finite dimensional vector spaces. Okay.
А что значит, то есть в чем заключается утверждение про locally a direct summand of G? Разве это не для любого расслоения верно? Не для любого локально свободного пучка?
Well, let's consider examples.
Ну, просто локально там, у нас же все афинное, поэтому все расширения, они...
So on the one hand, I cannot give a counterexample to lemma that I'm going to prove, but what the bad things that can happen we discussed already last time. So we consider y a fine line, H and G just the structure sheaf, and alpha is multiplication by coordinate t. Okay, then the rank of alpha y is 1 when y is not 0, and the rank of alpha 0 is 0. Okay, and well, So at the level of invertible sheaves, this morphism alpha is an embedding, right? 0 goes to O to O goes to K 0. Okay. So particular alpha is an embedding, but at the level of fibers, it's not an embedding. At 0, it is just a trivial map. Okay. So that's what we're struggling with, and let me consider some better example. So now y is still the affine line, and the h is still the structure sheaf, but G is two-dimensional vector bundle. Okay, and then alpha, well, always any morphism from the structure sheaf to anything at all is just global section. Okay, so global sections of structure sheaf are polynomials in one variable. And here you have two copies of structure sheaf, so we'll have two polynomials in one variable. So alpha is the pair of P and Q, two polynomials in one variable. And so let me ask you, when the image of alpha is locally free and locally a direct summand.
Не
А
знаю.
что имеется в виду, когда...
Maybe the ideal generated by P and Q should be principal or something.
All the ideals in polynomials are principal, unfortunately.
In one variable.
Yeah, it's just one variable. Two generators, but still there will be one common.
Maybe P and Q, if they do not have the common divisor.
Absolutely. Yeah, they must be relatively prime. Absolutely, yes. So you see that the image is, well, unless P and Q are both 0, totally 0, identically 0, then alpha will be always an embedding. So its image will be just the structure sheaf and hence locally free. So this by itself imposes no condition. But as you rightfully claim, then this second condition is equivalent to the claim that the ideal generated by P and Q is the whole ring of polynomials. Okay, so they have no common zeros.
Действительно, спасибо.
Okay, thank you. So somehow that's what we're trying to prove. We're trying to prove something like this. Okay, and now let's actually go and prove it. So consider something, the co-kernel of alpha. Yes, so we have this morphism alpha from H to G, and we take its co-kernel. And then, since tensor product with the structure sheaf of point Y is right exact, the fiber of this kernel at Y will be just GY modulo the image of alpha Y, and we know that that this is constant, right? Because alpha has constant rank. So the dimension of GY is constant. Well, is in the, how to say, constant, independent of Y. But then we proved last year that it means that this co-kernel is sorry, not it. fiber, but the kernel itself is locally free. Okay, and as we saw in those examples, it doesn't mean much by itself, but we know that we have this exact sequence. 0 goes to the image of alpha, goes to G, goes to J, goes to 0. Okay, so locally J is free and G is free, but any morphism from anything to a free module has a section. Okay, so locally J is a direct summed over G. Okay, and that's what we wanted to prove. We wanted to prove something else, but this is the main part. Okay, since any morphism onto a free module has a section. So in other words, a free module is projective. Fine, and hence this alpha, the image of alpha locally is the quotient of G, but again it's of the constant rank, so it's locally free. So we continue in the same way, and the image of alpha is also locally free, and locally a direct summed of G. Okay. By the way, there's a very nice notation for this. We say that image of alpha is direct summed of G, and also J is direct summed of G. Okay, and similarly, we prove the same for the exact sequence 0 to the kernel of alpha, to H, to the image of alpha, to 0. Okay, and that's what we wanted to prove, right? We want to prove the image of alpha is locally free and locally direct summed, and the kernel of alpha is also locally free and locally direct summed. Okay. So it was some lemma for proving our proposition. Yeah. So let's go back and recall what we're going to prove. We're going to prove that the formation of direct images commutes with a base extension if we know that the cohomology, ith cohomology of fibers have the same dimension. Okay. So, well, once more, we had this Grothendieck complex KK, yeah, with differentials alpha, and we know the differentials of alpha I minus 1 and alpha I have the constant rank, so we can apply our lemma. So let's apply our lemma, and we see that there are exact sequences. The kernel of alpha I minus 1 goes to K I minus 1, and then goes to the image of alpha I minus 1, and also the same for number I. And finally, for the definition of cohomology, sorry, to
Можно спросить?
our ith direct image, yes? Yes.
Ну, говорит, индейка, вот в последней точной последовательности у нас стояла не f, а опять тоже тензорное произведение про область.
Yeah. You're asking for something more general, and we will get there. But so far, there is no extra sheaf M, or if you wish, this M is just structure sheaf on Y. But we will have it in a minute. Okay, now we're dealing with a particular case when M is trivial. Okay. Okay. So from lemma, these are all locally split. Okay, and everything here is of constant rank, and they're all locally free. Okay. So in particular, the ith direct image is locally free, and since they're all locally split, it means that well, that all these sequences remain exact after tensoring with M. Okay, and that's what Sergey asked. So we get that the direct image of F tensor pullback of M is isomorphic to the direct image of F tensor with M. So it commutes with base extension. Okay. Fine. So we proved this proposition, and now let's prove another corollary, another proposition.
Could I ask
Yes.
a question?
Yes.
In your example of when alpha is a morphism from a structure shift to the direct sum of two
Yes.
structure shifts, when if the map is two polynomials, suppose they have a common divisor, then why alpha is not locally a direct summand of the direct sum shift? How can we see it in example?
But you see, if it were direct summoned locally, then the quotient would be also locally free, right? I have let's write it here. So I have O to the structure sheaf. It is embedded into two copies, P and Q, and there is some quotient, Q goes to 0. So if well, it's also alpha. If alpha was an embed, if alpha were an embedding of well, of a direct summand, then the remaining direct summand would be just another copy of the structure sheaf, right? Just an invertible sheaf. Okay, but if P of something of A equals Q of A equals 0, then the co-kernel of alpha has torsion at point A. Okay. So
hence
it
is not
locally free.
Не, я
So
все-таки не
unit
понимаю. То есть,
of alpha, yes.
если мы это расширение рассмотрим локально,
a sum and direct sum.
то оно представляет какой-то элемент x1. А x1 у нас равен нулю локально. Поэтому оно расщепляется.
X1 of what? X1 of what? It's an X1 from quotient to sub, right?
Yes.
But the quotient will have torsion. The quotient will have torsion. That's the problem.
And then x1 will be non-zero, yes?
In particular, yeah. Mm-hmm.
Okay.
Another example of the structure sheaf. Okay. So did I answer your question? Hopefully, yes. Okay. So let's go on to another proposition. Another corollary. So assume you have a point in the base such that the cohomology of the corresponding fiber vanishes in certain degrees. Okay, and then it is claimed that in some neighborhood of y, this Grothendieck complex can be taken of length p. Zero goes to k0, goes to so on, goes to kp, goes to 0, and that's it. Okay, so the length is we only know that it's bounded, but we don't know the exact bound. But here is an exact bound. Okay, and also we know that the higher direct images of our sheaf are 0 for I bigger than p. That's the same range, and the highest non-vanishing direct image RP commutes with base extensions. Okay. So let's prove this. And well, certainly we start with with some Grothendieck complex. Say of length n. But we want to prove that this n is just p. Okay, so well, if n happens to be p or less, then we are in business. But if n is bigger than p, then we need to somehow cut or truncate our complex, and that's what we'll do by induction.
А если n меньше p, то почему все доказано?
Well, maybe not quite, but at least part A is proved. Yeah. So let's prove first part A, and then we want to prove that k can be chosen of small length. So if its length is already small, there's nothing to prove. So if n is bigger than p, then we want to truncate k and proceed by also to say descending induction. Okay. So how do we approach this? Well, we know that the co-kernel of alpha n minus 1, the fiber at y, is isomorphic to the nth cohomology of our fiber, and is 0. Okay, but by assumption. And this means that alpha n minus 1 is surjective in some neighborhood of y. Okay, so let's shrink y to this neighborhood and assume that alpha n minus 1 is onto okay. Oh, sorry, it's not I, it's n, n minus 1 to n. Sorry. Okay, and then again, locally, well, even not locally, our k's are assumed to be free, right, in Grothendieck theory. So there's a projection onto a free module, and again, it has a section. So Kn is a direct sum of Kn minus 1, and so we have a projection to the complementary summand. So we have this embedding K n into K n minus 1, and then the corresponding quotient to K n minus 1 nu. So we're going to consider this new complex of length n minus 1. But well, this new thing is locally free, but again, shrinking y, we can assume that it is free.
Чем вот этот новый комплекс лучше старого?
Why is it better? That's what you ask?
Да,
I
почему
just-
нам потребовался новый комплекс для доказательства теоремы?
Well, we are trying to prove that there is no cohomology. Well, the complex can be chosen of small length. Yeah, that's our point. Point A. That's what we need to prove. So we're gradually, well, cutting the length by 1. Yeah, from n to n minus 1, and then if n minus 1 is still bigger than p, we'll go to n minus 2, and so on.
Спасибо.
Welcome. So this new guy is free, and it's the image of Kn minus 1. So we can consider the new complex. K0 to so on goes to K n minus 1 nu. And well, say here before we had K minus 2 old. Like this, and you see there is a projection from the old complex. K0 to so on to Kn minus 2 to Kn minus 1 to Kn 0, and there is a projection that there's just identity everywhere here, but this projection there and going to 0 here. Okay, and they're quasi-isomorphic. So it's a quasi-isomorphism. But because it is an embedding of that direct summand, this commutes with tensoring with anything. K nu is a direct summand of K. But this embedding direct summand is a quasi-isomorphism. It means that K nu tensor M is a direct summand of K tensor M, and again this is a quasi-isomorphism. Okay. Fine. So this takes care of A. And now I have to prove B. So we know that.
I'm sorry, could
Yes.
they
Yes.
ask? I did not miss.
Sorry. Yes.
I did not miss at the beginning when you conclude from. You said that if co-kernel of the map alpha y and -1 is 0, you conclude that there is a neighborhood such that alpha restricted to this neighborhood is surjective.
Yes.
Yes. Why it is so?
Because taking fibers is right exact, right? So you consider the co-kernel. You know that this co-kernel has 0 fiber at point y small, right? But if a coherent sheaf has a 0 fiber somewhere, then it vanishes absolutely in some neighborhood of this point. We proved this last year as well. Yeah.
And okay.
So the fibers can only jump under specialization. So if some fiber is 0, then all the nearby fibers are also 0 a fortiori. So the sheaf is totally 0 in some neighborhood. Okay.
And the last step, when you tensor on M, you said that M can be anything here.
Absolutely, any quasi-coherent sheaf on Y. Yes.
Why?
Yes.
I know that
well,
if
just because we have
tensor is right.
Absolutely, but here we deal with direct summand of free complex, which is quasi-isomorphic. Yes. So
I don't understand this fundamental property use. If this K nu is direct sum, then we can tensor by anything.
yeah. Well, I don't know how to say it. K nu plus some junk is equal to K, and everything here is free. Okay, and this is quasi-isomorphic to 0, so it's acyclic and locally free. Well, and free. Okay, so it means that K nu tensor M plus J tensor M. Sorry. Equals K tensor M, but this guy is still acyclic. Yeah, because it was acyclic and free, we tensor it with anything, it's still acyclic. Okay, so K nu and K tensor M have the same cohomology because they differ by some acyclic sum.
Thanks.
Welcome. Okay, so I forgot where were we? We're going to prove B, yeah, or something else. We proved A, yeah, and we wanna prove B. Well, we take the ith cohomology of our Grothendieck complex. Okay, so for big degree I that is bigger than P, the Grothendieck complex just vanishes in this degree, and then the higher direct image also vanishes. And well, that's what we wanted to prove. Yeah, if you remember B. So we want to prove that in degrees higher than P, there are no higher direct images, and in P's degree, the P's direct image commutes with Bayes extension. So that's what remains to be proved. And P's extension, sorry, P's direct image of F tensor pullback of M is isomorphic to the kernel of alpha P minus 1 tensor M, and this is the same as co-kernel of alpha P minus 1 tensor M, but just by right exactness. Of tensor product. Okay, and this is just, as we know, the P's direct image of F tensor M. So we're done. Fine. And now the last application, the third and the last application, that there is a coherent sheaf Q on Y such that we have an isomorphism, canonical isomorphism, local homomorphism, or maybe underlined, from Q to any M is isomorphic to the push forward. It's the zero higher direct image. Yeah, just push forward of F.
Что означает подчеркнутый home?
Just local home. Well, it's a coherent sheaf on Y, not a vector space or whatever module over regular functions, but just a sheaf.
Спасибо.
Okay, so for any M quasi-coherent on Y. So let's prove this. And
F заранее задан, да?
Yes. So we have, as always, so we have projective morphism from X to Y and a coherent sheaf on X, just as before. Okay, and under these circumstances, the zeroth direct image can be computed just as a home from some quasi-coherent sheaf on Y. Oh, sorry, from some coherent sheaf on Y. Okay, so the proof will be ideologically similar to the construction of a Cartesian product. If you remember, we had this last October, something like this, and well, you see, this Q represents certain function. Yeah, you expect this canonical isomorphism, and the right-hand side is certain functor in M. Okay, and the left-hand side is certain functor in M. So you need to find the representing object for the right-hand side functor in M. Yeah, and certainly this representing object is defined canonically, uniquely, by Yoneda or whatever. So we only need to construct it locally. If we manage to construct it locally on Y, then it will necessarily glue on the intersections, just because of this uniqueness by Yoneda. So the representing object Q is necessarily unique. So suffices to prove its existence locally, and it will automatically glue on the intersections. Okay. So locally we have this complex. Mm. 0 goes to K0, sorry, goes to K1, and so on, such that the push forward of of F tensor, the pullback of M, is isomorphic to the zeroth cohomology of this complex, that is just to the kernel of alpha naught tensor M. Okay. So we just set Q is the co-kernel of the dual complex alpha naught dual from K1 dual to K0 dual. So then we have the exact sequence homomorphisms from K1 dual to M, homomorphisms from K naught dual to M, and well, sorry, homomorphisms from Q to M, 0. And here you have just how to say alpha 0 dual. Well, if you want the tensor identity of M, and this is nothing but since K is just a free module, the homomorphism from the dual of K is nothing but K1 tensor M, and here again it's the same as K0 tensor M, and this map is just alpha 0. Well, again, to tensor the identity of M. Okay, so from this we see that homomorphisms from Q to M are just the kernel of alpha naught tensor M, and this is the same as we know the push forward of F tensor pullback of M. Okay, that's what we wanted. Fine. So we proved those basic propositions, and we will use them from now on. Now we turn to nice application. So we developed somehow everything we wanted to develop, and now we'll only derive some pure pleasure from this. Okay. So.
Можно спросить?
Yes.
А вот почему Гретендику понадобилась вот такая теорема, которую вот мы доказывали глобально как-то? Она ему была вспомогательна или она сама по себе интересна?
Well, we have already seen some propositions, corollaries of this theorem, and certainly Grothendieck had them in mind. But well, he wanted to compute the higher direct image sheaf, and we will also need these computations later on. You will see, but at least it gives you some conditions when those higher direct image sheaves behave nicely, just as vector bundles. Yeah, and when they commute with the base extension, so they allow you to compute cohomology of fibers.
Спасибо.
Okay. Well, it is very close to well, something called the Zariski theorem on formal functions. Well, but again, we'll turn to this maybe in a week. Okay, so maybe in a week it will become clearer how to use it. Okay. So we start with some lemma about finite morphisms, and if you remember when we introduced finite morphisms last October, we immediately proved that that the fibers of a finite morphism are all finite, and that's why the name is finite morphism. Okay, and now we are going to prove some converse statement. Well, you know that in general it's not true. So say you can take an open embedding. Yeah, an open embedding has all the fibers is either one point or empty at all, but it is never a finite morphism. Well, unless it's an isomorphism. Okay, but if you know in advance that your morphism is projective, then it's enough. So if you have a projective morphism that has finite fibers, then it's necessarily finite. And that's the content of this lemma we're going to prove. So we have a projective morphism. And you know that all the fibers of F are finite. Then we can conclude that F is finite. Okay. So, well, we need to check that f is affine, because then x will be the relative spectrum of the direct image of its structure sheaf, and the structure sheaf will be a finite OY algebra, so the X will be a finite morphism. Okay, so how do we do this? It's a local claim. So we can shrink y as we please, and we take a point around which we want to consider our problem, and we need an affine neighborhood of this point, such that its preimage is affine such a variety in X. Okay, so we now recall that X was projective, so we had an embedding. X was closed in Y times some projective space. Okay, and then we're going to project it to Y, and this was our F. Okay, so we know that the fiber over Y, over small y point, is finite by assumption. Say finite set, but it's finite subset of this ambient projective space. Okay, and since it's a finite subset of the ambient projective space, we can find a hyperplane that avoids all the points of F. Say L equals 0, avoiding F, finitely many points. So in other words, this whole fiber lies in the corresponding open set, BL. Sorry, yeah? The basic open set. And it's also a phi. And somehow that's the reason we'll be able to succeed. Okay. And let's consider open subvariety U. So this U is X intersected with Y times this open DL. Yeah, so it's open in X. And well, so you see, X was a closed subvariety in Y times Pn, right? And now you replaced Y times Pn by Y times DL. So we might assume that Y is affine because our question is local. Yeah, assuming Y affine, Y times DL also affine. and x intersected with y times dl is closed in y times dl, and hence this intersection, or in other words, u, is affine. Okay, and now let's set another open subset. W is the complement to y without f of the complement to u. So the complement to u is closed, and f is projective. So f of x minus u is also closed. So it's open in y, since f of x minus u is closed, and this is in turn since f is projective. Okay. Okay, so W is open, and so certainly it contains our point small y by construction, and also the preimage of W is contained in open U. Okay, so take a regular function phi on y, such that the basic open subset d phi is contained in W, and then well, that's it. So the desired V, we started with the desire to find a neighborhood V, yeah, in the very top of this page. We wanted a neighborhood V whose preimage was affine. So this V is just this basic open subset d phi. Since the preimage of V is the basic open subset phi composed with F, well, in U. Okay, and that's a phi. So there we are. And this lemma by itself does not use anything at all. Yeah, we could have proved it last October, something like this. Well, we needed the notion of projective morphism. As soon as we had projective morphisms, we could have proved this lemma. Okay, but now, granted this lemma, we can prove the Kodaira theorem. Embedding, well, criterion if you want. But somehow its formulation is a little bit faulty at our level. So we start already with projective variety, and this is what I don't like. Unfortunately, and we have an invertible sheaf on X. And we have some finite dimensional subspace in global sections. So V in global sections of L is well, a finite dimensional subspace. And if you remember, we discussed it at some point. it defines at least a rational map from X to the projectivization of V dual, like this. Namely, each point X goes to the hyperplane in V, formed by these sections vanishing at this point. Okay. So this is only a rational morphism, because it can happen that for some point X small in our variety X, all the sections of this vector space vanish at this point. Yeah, in principle, it can happen. Then this point is called the base point of this linear system. And then this map is not defined at such a base point. But now I formulate the Kadaira conditions. First of all, this map is regular. So if, first of all, for any X, there is a section sigma in V such that sigma of X is not 0, then this map is regular. It is well defined. Maybe let me call it phi. So if so, then phi is regular from X to the projective space. Now, furthermore, if for any two distinct points their images are distinct, so there exists a section sigma such that sigma, say, of X is 0, but sigma of Y is not 0. Okay, so the corresponding hyperplanes are different. And then your phi is sort of a pointwise embedding, but not necessarily embedding in the algebraic sense. And finally, the third condition is that for any point, if we consider the hyperplane of sections vanishing there, Lx set of sections sigma X is 0. Okay, so this hyperplane is sort of say big enough. The differentials, well, has the following property. So the differentials at X for sigma in this hyperplane span the whole tangent space. But since we also have the sections of this, not just functions, but sections of this line bundle, so we need to tensor by the fiber of this line bundle, and well, this is the image of sigma
Не понял, почему потребовалось еще умножить на линейное?
Because, well, if you have a function, then its differential lies in the maximal ideal modulate square, right? But our sections are not functions. They are only locally, non-canonically functions. And globally, they are sections of line bundle, right? So they're not functions. They're, so to say, twisted functions. And we have to use this twist.
And did we have a notion of Durand differential for bundles, not for functions?
But I'm defining it right now.
Ah, okay.
So that's what I mean. Okay. Yeah. So the condition B means that two distinct points go to two distinct hyperplanes, and condition C is sort of the same condition, but for distinct points that are infinitesimally close. So it's an infinitesimal version of B. Okay. So if all these conditions are satisfied, then phi is a closed embedding from X into projectivization of this space. So in other words, we ended up with X being a projective variety. And that's what is unsatisfying for me in this formulation. So we started with a projective variety, and under certain conditions prove that it's a projective variety. Well, we constructed some particular projective embedding, knowing that it's an abstract projective variety, but still, I don't like this formulation. Originally, Kadaira formulated his theorem for scalar varieties, complex scalar, well, compact complex scalar varieties, and then you don't know in advance that that they are projective. In fact, there is a lot of non-projective scalar varieties. Okay, but Kodaira found the criterion when a compact scalar variety is projective, and this is an algebraic reformulation of his criterion. But somehow we need to know in advance that our variety is projective. In fact, certainly you don't need it's projective. It's enough that it's proper. Okay, but then in the previous theorem we would need to use properness, and it'll be a pain in the neck because you would need to have this Chow dominating morphism. So it's also true that if you have proper morphism with finite fibers, then it's finite. But the proof is harder. Okay, now we have 2 minutes. I don't know. What shall I do? Maybe I shall skip. So the proof is not long, but not 1 minute. So maybe I will not formulate this theorem with Kadaira embedding criterion next time. I will assume we know this formulation and prove it next time, the first thing. Okay, and in particular from this criterion, it will be immediate that the canonical line bundle defines an projective embedding of a curve into projective space, unless your curve is hyperelliptic. Okay, so either your curve is hyperelliptic or it is embedded by canonical line bundle. In fact, you can take, say, the square of canonical line bundle, and it will always embed your curve into projective space. So if you want something universal, then just take omega squared.
Squared or cubed?
Okay, let it be cube. So I mean, if your curve is not P1 or elliptic, then the omega cube certainly will give rise to projective embedding. And well, maybe it somehow justifies this formulation of Kadaira theorem because we already knew in advance that all the proper curves were projective, right? But now we will be able to deduce some concrete projective embedding given by the third power of canonical bundle. Okay, so that's it. Any questions?
Can I ask,
Yes.
if L here invertible sheaf has negative degree, then
this thing will never happen. Well, I mean, it will, roughly speaking, have no sections at all. So you see here, we need many sections. And
you need a condition on L at the beginning that it has positive degree. No.
No, I don't need to impose this condition as an extra condition, because I started with a fundamental vector subspace in global sections that was pretty ample, that had many sections. These sections, they distinguish between points and infinitesimally distinguish between points.
But this
so you need many
gamma
sections.
will be empty, and we cannot embed X. The projectivization.
If gamma is empty, this definitely cannot happen. So I need three conditions, A, B, C. If they are satisfied, then we will have projective embedding. But
and from these three conditions,
at all, then certainly you cannot satisfy even A, not to mention B or C. Yeah.
And I said when we need how to define the power of tensor power of the invertible sheaf,
yes,
such that it will be very ample.
First of all, it's not always possible. Yeah, there are certain sheaves that are not ample in any power at all. No matter how high power you take, it's never ample.
Okay,
then
for
what is
curves.
your question? Well, for curves, it's just the question of degree. There is no problem. For curves, it's very easy. But starting with surfaces, it's very hard.
It is a question for curves. It will be determined from Riemann-Roch theorem.
For example, if your degree is bigger than whatever 6G, I don't know, then certainly it will satisfy this Kadayara criteria.
Должны выполняться все три условия одновременно или?
Oh yes, certainly. Yeah. Well, it will be clear when I prove it, but say the BB is manifestly necessary, because it says that the different points go to different hyperplanes, and the condition C is the same, but at the infinitesimal level. So the differential of this morphism is an embedding.
Спасибо.
Welcome.
Could you
yes.
Could you give an example of non-base point free line bundle? It will not satisfy the A condition. Yes.
Well, maybe I don't want to say anything clever at this moment. If it has not enough sections, then they cannot distinguish the points. Yeah. So if your variety is 5-dimensional, but the space of sections is 4-dimensional, then it certainly cannot distinguish the points. There are some much more interesting examples, but even this stupid thing suffices.
Okay, thanks.
Yeah. Okay, so then let me save the notes. And if there are no more questions, let me stop the recording.